a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. In this episode, we take a calm tour through the main ideas people have proposed as alternatives to the Big Bang story. We look at what the Big Bang model actually claims, what evidence made it popular, and where the open questions still are. Then we explore other models that try to explain the same sky with different beginnings, different cycles, or sometimes no beginning at all. We cover steady state and its modern cousins, cyclic and bounce cosmologies, plasma and electromagnetic ideas, proposals like tired light, and more recent frameworks like conformal cyclic cosmology and ekpyrotic models. Throughout, we keep a simple standard in mind. What does the idea predict? What would count as a test, and where does it struggle? Tonight, we go through alternatives theory to the Big Bang. You can imagine the universe as a story told in light. Every night, as the planet turns, we see that story overhead. Some of it is bright and close, like the moon or the planets. Some of it is so distant that what we see is not the present, but the deep past. When a telescope collects faint photons from a far galaxy, it is catching a message that has been traveling for millions or billions of years. Cosmology is the attempt to read those messages and build a picture of the whole. It asks the biggest questions in science. What is the universe made of? How did it get its structure? Is it finite or endless? Did it have a beginning? Will it end? The most famous answer in modern science is the Big Bang model. In everyday language, people hear the phrase and picture an explosion in empty space. But that image is not what the model actually says. In the simplest terms, the Big Bang story is not a bomb going off inside space. It is space itself changing. It says that the universe was once in a hot, dense state, and that over time it expanded and cooled. As it cooled, matter formed, atoms formed. Light that was once trapped became free to travel. Later, gravity gathered matter into stars and galaxies. If you have heard about expanding space, you have heard the core idea. When astronomers look at far galaxies, they find that the light is redshifted. The wavelengths are stretched. The farther away the galaxy is, the stronger the redshift tends to be. The most common explanation is that space has expanded while the light was traveling. The light was not slowed. The space between things grew. The Big Bang model also points to a faint background glow in the sky. This is the cosmic microwave background, often shortened to CMB. It is a nearly uniform bath of microwave radiation coming from all directions. It is incredibly smooth, but it has tiny variations, tiny temperature differences that map out early density ripples. In the Big Bang story, the CMB is leftover light from the early hot era, released when the universe cooled enough for electrons to combine with nuclei, making neutral atoms. Before that, the universe was like a fog of charged particles. Photons bounced around constantly. After neutral atoms formed, the fog cleared and light could travel long distances. That released light has been stretched by expansion and cooled into microwaves. There is also the abundance of light elements: hydrogen, helium, and a small amount of lithium. The Big Bang model says that in the first minutes, nuclear reactions in the hot early universe produced these elements in a predictable ratio. Astronomers can measure helium fractions in old gas clouds and in old stars. The numbers broadly match the model. When you put these pieces together, you get a powerful picture: expansion, a background glow, a a chemical fingerprint. So why talk about alternatives? Because science does not run on slogans. It runs on questions. The Big Bang model is not a single, finished theory. It is a framework with many moving parts and many open problems. When people say Big Bang, they often mean a package deal that includes dark matter, dark energy, inflation, and a certain timeline of cosmic events. Some of those pieces are inferred rather than directly observed. Dark matter has strong evidence in galaxy rotation, gravitational lensing, and large-scale structure. But we have not captured a dark matter particle in a lab. Dark energy is a name for the observed late-time acceleration of expansion, inferred from supernova brightness and other probes. We can measure its effect, but we do not know what it is. Inflation is another famous piece. It is a proposed brief period of extremely rapid expansion early on. It was introduced to solve several puzzles, like why the universe looks so uniform across vast distances and why space seems so geometrically flat. Inflation can also generate the tiny density ripples that later become galaxies. Inflation is widely used, but it is still a hypothesis with many versions. It can be hard to test directly because it happens so early, and different inflation models can be tuned to fit the same data. There is also the question of the beginning itself. Even if the early universe was hot and dense, what happened at the earliest moment? In general relativity, if you run the equations backward, you often reach a singularity, a point where the math breaks. Many physicists do not believe a true physical singularity is real. They suspect quantum gravity would change the story. So in practice, there is room to ask, is there another way to explain the redshift? Is there another origin for the CMB? Is there another path to the element abundances? Could the universe be cyclic? Could it be eternal? Could the early universe have been different? Alternatives are valuable even when they are wrong. They force the main model to sharpen. They make predictions. They point out assumptions. But not all alternatives are equal. Some are serious proposals developed by experts and tested against data. Others are more like ideas in the public imagination. Some are linked to misunderstandings, like thinking expansion requires a center. Tonight, we are going to sort them calmly. We will start by slowing down and asking what counts as an alternative. An alternative can mean different things. It can mean a different explanation for the same observations. For example, if you accept that galaxies are redshifted, you might reject expansion and propose a different cause of redshift. Or it can mean a different picture of the early universe, while still accepting expansion. For example, you might accept that the universe expanded, but disagree on whether it began with a singularity or whether there was inflation. Or it can mean a broader framework that changes the basic rules, like modifying gravity or adding extra dimensions. To keep this clear, we can hold 3 questions. First, what does the model say about the large-scale evolution of the universe? Is it expanding forever? Is it contracting? Is it steady? Second, what does it say about the origin of the CMB and the observed redshift? Third, what tests does it offer? If a proposal does not offer tests, it may be more like philosophy than science. Now, before we step into steady state and cycles, it helps to remember a key fact about redshift. Light can be redshifted by several mechanisms. One mechanism is motion, the Doppler effect. If a source moves away, its light is stretched. Another mechanism is gravity. Light climbing out of a gravitational field loses energy and shifts red. Another mechanism is expansion of space. The light is stretched along with space. Another proposed mechanism is interaction with matter or fields as light travels, sometimes called tired light. The main modern view is that cosmological redshift is best explained by expansion. It matches the observed relationship between distance and redshift. It matches time dilation in supernova light curves. It matches detailed features in galaxy surveys. But the alternatives tend to attack this point. If you can explain redshift without expansion, you can rewrite the story. So let us look at one of the most famous alternatives historically: steady state. In the mid-20th century, before the CMB was discovered, there was a real debate about cosmic history. Some scientists disliked the idea of a cosmic beginning. They preferred an eternal universe that looks roughly the same at all times. The steady state model was developed by several prominent figures, including Fred Hoyle, Hermann Bondi, and Thomas Gold. It proposed what is called the perfect cosmological principle. Not only is the universe roughly the same everywhere on large scales, but it is also roughly the same at all times. If the universe is expanding, that seems to break steadiness. As expansion spreads matter out, the average density would decrease over time. Steady state solves this by proposing continuous creation of matter. As space expands, new matter is created so that the average density stays constant. In this view, there is no beginning. Galaxies form continuously. The universe is always about the same. This might sound wild, but it was not a random guess. It was a structured idea. It made clear predictions. One major prediction was that the universe should look similar at different distances, which correspond to different times. If the universe is truly steady, the number of galaxies, their types, and their distributions should not change strongly with redshift. As observations improved, astronomers began to see evolution. Distant galaxies look younger. Quasars are more common at certain redshifts. Star formation rates change over cosmic time. Then came the CMB. A steady-state universe has a hard time producing a nearly perfect blackbody microwave background with the observed spectrum. You can try to produce background radiation from starlight scattered and thermalized by dust, but the match to the CMB spectrum is extremely precise. The CMB is one of the strongest blows to classic steady state, so the classic model fell out of favor. But in science, ideas often return in modified form. There are modern versions, sometimes called quasi-steady state or cyclic steady state, which try to keep an eternal universe while admitting that there can be changes and cycles. One example is the quasi-steady state cosmology proposed by Hoyle, Burbage, and Narlikar. In this view, there are episodic creation events rather than continuous creation. The universe oscillates in scale with cycles of expansion and contraction on top of a long-term steady behavior. They attempted to explain the CMB as thermalized starlight from many cycles with specific dust properties. These models are not mainstream, and they face strong observational challenges, but they show a pattern. Even when a model fails, the desire for an eternal universe can survive. Now, in a different corner of cosmology, there are cyclic models that are more tied to modern physics. Cyclic and bounce cosmologies. A cyclic model says the universe goes through repeating phases: expansion, then contraction, then a new expansion. If you imagine a breathing cosmos, that is the idea. A bounce model is a related idea. It says that instead of reaching a singularity, a collapsing universe can bounce into a new expansion due to quantum effects or new physics. These ideas are attractive for several reasons. They can avoid a singular beginning. They can potentially explain why the universe is large and smooth, because repeated cycles could smooth out irregularities. They can offer alternative explanations for the origin of cosmic structures, but they also face hard problems. One major problem is entropy. In everyday physics, entropy tends to increase. If the universe cycles, entropy would accumulate from cycle to cycle, making each cycle longer and larger. That could still be possible, but it changes what eternal means. You might have a past with cycles that are smaller and shorter. Another problem is how to get a clean bounce. In general relativity, if you fill the universe with normal matter and energy, contraction tends to lead to a singularity. To bounce, you need something that violates certain energy conditions, or you need modifications to gravity or quantum geometry effects. Let us take one famous cyclic proposal tied to string theory, the ekpyrotic and cyclic ekpyrotic models. In some versions of string theory, our universe could be a three-dimensional brain embedded in a higher dimensional space. Another brain could exist nearby. A collision between brains could release energy and create what looks like a hot Big Bang-like state. In this picture, the Big Bang is not the absolute beginning. It is a transition event, like a collision. Ekpyrotic means conflagration, like a great fire. The model can be built to produce a nearly scale invariant spectrum of density perturbations, similar to what inflation produces, but through a contracting phase rather than a rapid expansion. In some cyclic versions, brains repeatedly approach and collide, producing repeated hot phases. These models have been studied seriously. They have mathematical structures. They can be compared to CMB data. They have also faced criticism, and the space of possible versions is complex, but they represent a real attempt at an alternative early universe story. Another modern approach is loop quantum cosmology. Loop quantum cosmology is a simplified application of loop quantum gravity to the whole universe. In these models, the geometry of space is quantized. When you run the universe backward, instead of reaching infinite density, quantum effects become repulsive at very high density and cause a bounce. In this picture, our expanding universe might have been preceded by a contracting phase. One of the appeals is that it is a concrete mechanism that avoids a singularity without requiring a special inflation field. However, the detailed predictions depend on assumptions, and connecting loop quantum cosmology to observable data is an ongoing challenge. There is also a broader class of bounce models tied to modified gravity or exotic matter fields. Now, one of the most interesting alternative frameworks in recent decades is something called conformal cyclic cosmology. Conformal cyclic cosmology, often shortened to CCC, is associated with Roger Penrose. In CCC, the universe is divided into aeons. Each aeon begins with a hot Big Bang-like state and ends with a very cold, very empty, exponentially expanding universe. Penrose focuses on a property called conformal structure. Roughly, it is what remains of space-time when you ignore overall scale. In the far future, if the universe expands forever, matter can decay, black holes can evaporate, and the universe can become dominated by radiation and extremely low-energy particles. In such a state, there may be no meaningful mass scale. Without mass, the idea of a physical ruler becomes less defined. Penrose argues that the end of one aeon can be conformally matched to the beginning of the next. So the universe can cycle, but not by contracting into a bounce. It cycles through conformal matching of an infinitely expanded future into a new beginning. CCC makes some claims about possible observational signatures in the CMB, like circular patterns. There have been debates about whether the data supports these claims. Most analyses do not find strong evidence, but it is an example of a creative alternative that still takes the CMB seriously. Now, up to this point, many alternatives still accept expansion and a hot early phase in some form. They modify the beginning, not the fact of an early hot stage. Other alternatives are more radical. They challenge expansion itself, or they challenge the interpretation of redshift. This leads us to tired light. Tired light is a broad label for ideas where light loses energy as it travels through space, shifting to red without requiring expansion. You can picture photons gradually giving up energy to some medium or field. At first glance, this can seem simple. If redshift increases with distance, maybe it is because the light traveled farther and lost more energy. But tired light models face strong observational problems. One problem is time dilation. In an expanding universe, time intervals from distant objects should appear stretched by a factor related to redshift. When astronomers observe distant supernovae, the light curves are time dilated. They evolve more slowly, in a way consistent with expansion. A simple tired light mechanism would not automatically produce this time dilation. Another problem is image blurring. If photons lose energy by scattering off particles, the scattering would likely change their direction and blur images. Distant galaxies would appear fuzzier than they do. There are also detailed spectral features. Expansion stretches the entire spectrum cleanly. A scattering process could distort the spectrum. Some tired light variants try to avoid scattering by proposing interactions that do not change direction. But then you must define a new physics process that is very carefully tuned. Tired light is often discussed in popular alternative cosmology circles, but it is not considered a strong scientific competitor to expansion. However, the broader lesson is important. If you want to build an alternative, you must match not just the redshift distance relation, but the whole bundle of evidence that supports expansion. Now let us step into another alternative tradition, one that focuses on electricity and magnetism. Plasma cosmology and electromagnetic universe ideas. Most people learn that gravity shapes the universe on large scales, but the universe is full of plasma, which is matter in an ionized state. Stars are plasma. Interstellar gas is often plasma. Plasma responds strongly to electromagnetic fields. In plasma physics, you can get filamentary structures, currents, and complex behavior. Plasma cosmology is an approach that emphasizes the role of plasma and electromagnetic effects in shaping cosmic structures. There is a serious scientific field of astrophysical plasma physics. It is vital for understanding solar flares, jets from black holes, and magnetized gas in galaxies. But plasma cosmology, as an alternative to the Big Bang, is a different thing. It tries to build a cosmic history without a hot beginning, often proposing an eternal universe where plasma processes generate structures. Some proponents argue that the redshift might have non-cosmological components, or that the CMB could be explained differently. The mainstream view is that while plasma effects are extremely important in many contexts, They do not replace the evidence for a hot early universe. The CMB spectrum, the acoustic peak structure in the CMB, and the success of Big Bang nucleosynthesis remain major barriers. Still, it is worth understanding why electromagnetic ideas attract people. They offer a sense of active processes, visible filaments, and dramatic phenomena. They can feel more intuitive than invisible expansion. But intuition is not enough. The question is whether the model can reproduce precision measurements. Now, there is another family of alternatives that does not deny expansion, but changes how gravity works. Modified gravity and alternatives to dark matter or dark energy. Some objections to the standard cosmological model are not about the Big Bang, hot beginning, but about the extra ingredients. Dark matter. Dark energy. If you can explain galaxy rotation curves and cosmic acceleration without unseen substances, you might still accept a Big Bang like early universe, but you would have a different physics. One famous modified gravity idea is MOND, modified Newtonian dynamics. MOND proposes that at very low accelerations, the effective force law changes. This can explain the flat rotation curves of galaxies without dark matter. MOND has had some success at galactic scales, but it struggles at cluster scales and in cosmology without additional components. There are relativistic extensions of MOND, like TVIS, that try to make it compatible with relativity. There are also broader modified gravity theories, like FR gravity, scalar tensor theories, and others. Similarly, some alternatives to dark energy propose that the acceleration is not due to a new energy component, but due to modifications of gravity or due to the effect of cosmic inhomogeneities on averages. These are active research areas. It is important to note something. Even if you replace dark matter or dark energy, you might still have a Big Bang type early universe. So some of these are not alternatives to the Big Bang itself, but alternatives to the full standard package. Now, let us return to a question that sits at the heart of these debates. What counts as evidence for a hot early universe? If you wanted to escape the Big Bang story entirely, you would need to explain at least 3 pillars. First, expansion and redshift. Second, the CMB. Third, light element abundances. Let us linger on the CMB, because it is often misunderstood. The CMB is not just any microwave background. It has a spectrum that is extremely close to a perfect blackbody, with a temperature of about 2.7 Kelvin. A blackbody spectrum is what you get when radiation is in thermal equilibrium with matter. The shape is precise. The CMB also has anisotropies, tiny variations, and those variations have a specific pattern of acoustic peaks. These peaks are like fingerprints of sound waves in the early plasma. The pattern matches a universe where baryons and photons were coupled, oscillating under gravity and pressure, then decoupling. Any alternative must reproduce this. It is not enough to say there is some microwave radiation from distant stars. The fit is too clean. This is why many alternatives either accept the CMB as primordial, or they propose very specific thermalization mechanisms. Now think about the light element abundances. In the early minutes of a hot universe, nuclear reactions would produce helium and deuterium. The predicted ratios depend on the density of baryons. The observed deuterium abundance in certain pristine gas clouds is a particularly strong constraint. Deuterium is fragile. Stars destroy it. So when you measure deuterium in very old, low metal environments, you can estimate the primordial deuterium. The numbers match Big Bang nucleosynthesis in a striking way. To avoid a hot beginning, you would need a different mechanism that produces the same abundances in the right ratios, without overproducing heavier elements. That is a tall order. So in many serious alternatives, the Big Bang is not fully rejected. Instead, the singular beginning is rejected, or inflation is replaced, or the far future is connected to a new beginning. This leads to a calmer and more accurate statement. Many alternatives are not alternatives to the fact that the universe was hot and dense early on. They are alternatives to the interpretation that the universe began at a singular moment and then inflated. Now, with that said, we can explore one of the most confusing words in cosmology: beginning. A beginning can mean several things. It can mean a beginning of expansion. It can mean a beginning of time. It can mean a boundary where our physics breaks. In many models, the Big Bang is a boundary, not an event inside time. If quantum gravity resolves the singularity, the boundary might become a transition. So an alternative can be a way of turning the boundary into a bridge. Now let us step through several more alternative ideas, and for each one, we will keep the same simple pattern. What is the idea? What does it explain? What does it struggle with? First, the idea of an eternal inflation or multiverse. This might sound like it is part of the Big Bang story, and it often is, but it can also be framed as an alternative to a single origin. In some inflation models, inflation does not end everywhere at once. Some regions stop inflating and form bubble universes like ours. Other regions continue inflating. This can lead to a picture where the overall inflating space is eternal to the future, and possibly to the past, depending on the model. In such a picture, our Big Bang is not the beginning of everything, but the local beginning of our bubble. This is less an alternative to the Big Bang, and more a change of scale. The Big Bang becomes a local event in a larger landscape. The challenge is testability. If other bubbles exist, can we see signs of collisions? Can we see imprints in the CMB? Some people have searched for such features. So far, nothing decisive. Another idea is that the universe could have emerged from a quantum fluctuation or from a quantum tunneling event, like the creation of a universe from nothing. These proposals are tied to quantum cosmology. They are hard to visualize because they involve a regime where time may not behave normally. They also carry philosophical weight because of the word nothing. In physics, nothing often means a vacuum state with laws and fields already defined. These models are debated, and they are not easy to test, but they are part of the menu of alternatives to a simple singular beginning. Now let us talk about a very common misunderstanding. Some people think the Big Bang model requires that the universe expands into something, like empty space outside the universe. But in the standard view, the universe is the space. There is no outside required. Expansion means that distances within space increase. You can think of it as a map where the scale changes, not an object moving through a larger room. This matters because some alternatives start from a false problem. If you imagine an explosion in a room, you might ask where the center is. In the standard model, there is no unique center. Every location sees distant galaxies moving away on average. So when evaluating alternatives, it is useful to separate them from misunderstandings. Now, in the public discussion, there is also the idea that the Big Bang is disproved. because galaxies are not flying apart like shrapnel. But again, the model is not shrapnel. It is a changing metric, a changing scale of space. Now let us return to steady state again and talk about how it failed. One of the cleanest tests against steady state came from radio source counts. If the universe is steady, the number of radio sources above a certain brightness should follow a specific relationship. Observations showed more sources than steady state predicted, implying evolution. Then the discovery of the CMB made it even harder. So steady state is a case study in how data can end an era. But it is also a case study in how a model can be bold. Steady state made a clear claim. The universe is the same in time. That can be tested. Many alternatives today are less bold and harder to rule out because they can be adjusted. This is a quiet danger in theoretical physics. If a model has too many knobs, it can be hard to falsify. So a good alternative must aim to be sharp. Now let us explore one more alternative that appears in popular discussion, and then we will shift back to the more serious modern candidates. The idea that redshift is not distance. Some people point to claims of quantized redshifts, or to associations between high redshift quasars and low redshift galaxies. In the 20th century, the astronomer Halton Arp argued that some quasars appear to be physically associated with nearby galaxies, suggesting that the quasars might not be at cosmological distances. If true, this would challenge the simple interpretation of redshift. The mainstream view is that these associations can be explained by chance alignments and selection effects, and that the overall evidence supports cosmological redshift. Quasars have absorption lines from intervening gas clouds at many redshifts, consistent with a long path through the universe. Gravitational lensing also supports the standard distance interpretation. But again, this debate shows the kind of crack that alternatives try to widen. If redshift does not map to distance, the timeline changes. Now let us take a breath. At this point, you might notice a pattern. Many alternatives are motivated by discomfort with a beginning, or with unseen components, or with the complexity of inflation. But motivation is not evidence. So how do cosmologists decide? They use multiple independent probes, supernovae, baryon acoustic oscillations, the CMB, galaxy clustering, weak gravitational lensing, element abundances, and they see if one model can fit all at once. The standard model, often called lambda CDM, does a remarkably good job. Lambda stands for dark energy in the form of a cosmological constant. CDM stands for cold, dark matter. It is not loved because it is pretty. It is accepted because it works. So an alternative must be compared to that standard. Now, we can explore a few more subtle alternatives, the kind that might adjust the story without throwing it away. One is the idea that there was no inflation, but some other mechanism produced the initial conditions. Inflation explains flatness and horizon problems by stretching space. But there are other possible ways. A contracting phase can also explain uniformity, because in a contracting phase, regions that are now far apart could have been closer and in contact. This is one reason ekpyrotic and bounce models are attractive. They offer an alternative to inflation for solving the horizon problem. However, they must also reproduce the observed spectrum of fluctuations and their statistics. Inflation tends to predict nearly scale invariant fluctuations with a certain Gaussian character. Some alternatives can match this, but often with additional assumptions. Another alternative is that the early universe might have had a varying speed of light. This is called varying speed of light cosmology. If the speed of light was higher early on, then distant regions could have communicated and equilibrated, solving the horizon problem without inflation. These models are controversial and require careful treatment because changing fundamental constants can break established physics, but they have been explored. Another related idea is that the laws of physics themselves may have changed over time, or that certain constants drift. These proposals face tight constraints from observations, but they exist as conceptual alternatives. Now let us spend some time on the idea of a universe with no beginning, but not by steady-state creation. There are models where the universe is eternal into the past, but has a long, slow phase that looks almost static, then transitions into expansion. These are sometimes called emergent universe models. In an emergent universe, the cosmos may have existed in a quasi-static state for an infinite time, then started expanding. This can avoid a singularity and a strict beginning, but it can be hard to make stable. Now, let us step into the question of geometry. The Big Bang model often assumes that on large scales, the universe is homogeneous and isotropic. That means it looks roughly the same everywhere and in every direction. This is supported by the smoothness of the CMB. But the real universe has structures, voids, clusters, filaments. Some people have proposed that if the universe is inhomogeneous enough, the average expansion could be misinterpreted, and effects like acceleration could be apparent rather than real. This is sometimes called back reaction. It is a complex area. The mainstream view is that while inhomogeneities matter, they are not enough to fully replace dark energy. But research continues. Now we should also mention that the Big Bang model is sometimes criticized because it is used as a shorthand for unknowns. People say Big Bang, but they really mean we have an expanding universe. We have a background globe. We have a model that fits many things. But we do not know what dark matter is. We do not know what dark energy is. We do not know the exact inflation mechanism. We do not know quantum gravity. This is not a failure. It is a map with blank areas. Alternatives often target those blank areas. Now, in a calmer view, the best role for alternatives might be to provide different paths through the unknown. A bounce might replace a singularity. A modified gravity theory might reduce the need for dark matter. A new early universe mechanism might replace inflation. But the pillars remain. Expansion is strongly supported. The CMB is strongly supported. Primordial nucleosynthesis is strongly supported. So the alternative landscape is not a free-for-all. It is a constrained garden. Now, since this is a quiet archive story, we can slow down further and talk through these alternatives with gentle clarity. Imagine you are in a room with a long table. On the table are models, like books. Each book has a title: Steady State, Bounce, Cyclic Brains, Loop Quantum Bounce, Conformal Cyclic Cosmology, Varying Speed of Light, Tired Light, Plasma Cosmology, Modified Gravity, Multiverse Inflation, Emergent Universe. Each book tries to answer the same set of questions, and each book has chapters of evidence. Now we will open a few of these books more carefully. Let us return to Bounce Cosmology and ask a practical question. If there was a contraction before our expansion, could we see it? In some models, information from a pre-bounce phase could leave imprints in the distribution of fluctuations. In others, the bounce would erase memory. So there is room for testability. For example, some bounce models predict different types of non-Gaussianity in the CMB, or different ratios of tensor to scalar perturbations. Inflation predicts a certain spectrum of primordial gravitational waves, often described by the tensor to scalar ratio. If we detect primordial B-mode polarization in the CMB, it would be a major clue. So far, searches are ongoing, and foreground dust is a challenge. But this is one arena where alternatives can be compared. Now, let us return to CCC. CCC suggests the end of the universe becomes the beginning of a new aeon. This is a poetic idea, but it also makes a specific claim. The very early universe might carry signs of events from the previous aeon, such as the evaporation of supermassive black holes. Penrose suggested these could create rings in the CMB. Studies have not found convincing evidence, so CCC remains speculative. But it has value as a reminder. The future can be part of the origin story. Now, a deeper question: why do people want alternatives? Sometimes it is because of philosophy. The discomfort with a beginning can be deep. Sometimes it is because of misunderstandings. Sometimes it is because of skepticism about inflation. Sometimes it is because of the mystery of dark matter and dark energy. And sometimes it is simply because science is not finished. The universe is not obligated to be simple, but our models are always approximations. Now let us address a common emotional idea. Some people say the Big Bang is just a theory. In everyday speech, theory can mean a guess. In science, theory means a coherent framework that explains data and makes predictions. The Big Bang framework is supported by evidence, but it is not complete. That is why alternatives remain interesting. Now here is another important point. Many alternatives are not widely accepted, not because of bias, but because of numbers. Cosmology is now a precision science. The CMB spectrum is measured to astonishing accuracy. The acoustic peaks are mapped. The distribution of galaxies is mapped. Supernova data is refined. To compete, an alternative must match this precision. This is why simple, tired light does not survive. This is why dust thermalization explanations of the CMB struggle. This is why steady state failed. And this is why the strongest alternatives today tend to be those that keep most successes and change one key piece. Now let us explore one last cluster of ideas. The Big Bang model includes a phase called recombination, when the universe became transparent. Before recombination, photons scattered off free electrons. After recombination, photons traveled freely. The CMB comes from that surface. Alternatives sometimes propose different timing or different physics for that transition. But again, the CMB peak structure is a hard constraint. Now there is also the issue of lithium. Big Bang nucleosynthesis predicts a certain amount of lithium. Observations of old stars show less lithium than predicted. This is known as the lithium problem. It might be due to stellar processes that destroy lithium, or due to systematic errors, or due to new physics. Alternatives sometimes point to this as evidence that Big Bang nucleosynthesis is wrong, but the deuterium and helium fits are still strong. So the lithium problem is an open question, not a collapse. Now, as we come toward a close, we can gather the calm conclusion. The Big Bang model is the best supported large-scale description of cosmic history we have. It explains a wide range of observations with a single framework, but it is not the final story. It has mysteries. It relies on components we do not fully understand, and it may hide a deeper origin that is not a singular beginning. Alternatives fall into several categories. Some, like steady state, are largely ruled out in their classic form. Some, like tired light, face strong evidence against them. Some, like plasma cosmology, highlight real physics but do not replace the full framework. Some, like bounce and cyclic models, offer serious ways to replace the singular beginning and possibly replace inflation. Some, like modified gravity, can change the need for dark matter or dark energy while keeping a hot early universe. Some, like CCC, offer imaginative links between the future and the beginning. And some, like multiverse inflation, expand the meaning of the Big Bang to a larger landscape. In the end, the universe is not a debate, it is a reality. Models are just our best attempts to describe that reality. The cleanest attitude is humble curiosity. Ask what a model predicts. Ask what would count as a failure. Ask what data we could collect. And keep the mind open, but not so open that precision falls out. As you rest, you can let these ideas drift like distant galaxies. A universe with a single beginning. A universe with endless cycles. A universe that changes laws. A universe that fades into a new aeon. And you, here, on a small world, listening. The sky above is silent, but it is full of messages. The answers are slow, and the questions are beautiful. Now we can take a longer, calmer walk through a few of the most important tests, because the details matter. If you ever want to know why cosmologists lean toward expansion instead of tired light, one of the simplest reasons is not a complicated equation. It is the way distant events look in time. When a type Ia supernova explodes, it brightens and fades in a fairly predictable pattern. The curve has a rise, a peak, and a slow decline. In an expanding universe, the whole pattern should be stretched in time by a factor of 1 plus z, where z is the redshift. That means a supernova at redshift 1 should look like it is running at half speed compared to a nearby one. Not because the explosion is slower in its own frame, but because the time between the photons reaching us is stretched. Astronomers have measured this. The light curves of distant supernovae are time dilated in a way that matches expansion. A simple, tired light mechanism where photons slowly lose energy but do not change their arrival timing would not naturally produce this stretching. To fix that, tired light models often need to add extra effects that mimic time dilation. That is possible in principle, but each added fix makes the model less simple, and it must still avoid blurring and spectral distortion. There is another test that is quiet but powerful: surface brightness. If the universe expands, then objects at high redshift should look dimmer in a very specific way, beyond the simple effect of distance. Their surface brightness falls with 1 pluses to the 4th power. This is called the Tolman surface brightness test. Observations are complicated by galaxy evolution, because galaxies were different in the past. But in broad terms, data favors the expansion picture over simple tired light. Then there is baryon acoustic oscillation, BAO. In the early universe, sound waves traveled through the hot plasma. Those waves left an imprint, a preferred scale in the distribution of matter. In galaxy surveys, that scale appears as a slight bump in how likely galaxies are to be separated by a certain distance. BAO gives a cosmic ruler. When you measure that ruler at different redshifts, you can trace the expansion history. This is one reason the standard model is so strong. It is not relying on one dataset. It has multiple rulers and candles pointing to the same general story. Now think about the CMB peaks again. The peaks are not just random bumps. They tell you about the density of baryons, the density of dark matter, and the overall geometry. They are a record of oscillations in the early plasma. If a model tries to replace the CMB with thermalized starlight, it must also reproduce those acoustic features. That is extremely difficult. This is why many serious alternatives do not try to replace the CMB. They accept it, then reinterpret the earliest stage. Now let us return to inflation, because in some sense, inflation is itself the biggest alternative within the Big Bang framework. When people first accepted a hot early universe, they still faced puzzles. The horizon problem is a question about uniformity. The CMB has almost the same temperature in all directions, but in a simple, non-inflationary Big Bang timeline, regions of the sky far apart were never in causal contact before recombination. They could not exchange heat or information. So why are they so similar? The flatness problem is about geometry. The universe appears to be close to spatially flat. In the equations, flatness is an unstable balance. Without a mechanism, small deviations from flatness would grow over time, making the universe strongly curved today. Yet it is not. Inflation addresses both by stretching space so much that any initial curvature is diluted, and distant regions were once close and in contact. Inflation also gives a mechanism for generating the seed fluctuations that become galaxies, through quantum fluctuations stretched to cosmic scales. But inflation comes with its own questions. What field caused it? Why did it start? Why did it end? Why did it produce the specific amplitude of fluctuations we observe? And in some versions, inflation can become eternal, producing a multiverse, which raises the question of whether some parameters are selected anthropically rather than predicted. So alternatives to inflation are not fringe. They are part of serious cosmology. Bounce and ekpyrotic models, varying speed of light models, and some emergent universe models all attempt to solve horizon and flatness in different ways. Now, we can examine one specific comparison that is often used. The pattern of CMB fluctuations is not only about their strength, it is also about their statistics. Inflation tends to predict nearly Gaussian fluctuations, meaning the distribution of temperature variations is close to a bell curve with small deviations. It also predicts that fluctuations are nearly scale invariant, meaning they have about the same strength on different length scales, with a slight tilt. The data shows a nearly scale invariant spectrum with a slight tilt, consistent with many inflation models. Bounce and ekpyrotic models can also produce a similar spectrum, but often with different predictions for non-Gaussianity or for the tensor contribution. So one of the cleanest hopes for distinguishing models is a future high-precision measurement of primordial gravitational waves. If we detect them in a way that matches simple inflation, it would strengthen inflation. If we find limits that exclude many inflation models while supporting alternatives, it would push the other way. For now, the story is not finished. Now let us talk about a quieter reason people look for alternatives. The feeling that the standard model is built on invisible pieces. Dark matter and dark energy together make up most of the energy budget in lambda CDM. That can feel unsettling. But it is worth remembering that invisible does not mean imaginary. We do not see neutrinos easily, but they are real. We do not see magnetic fields directly, but they are real. In cosmology, we infer dark matter from its gravitational pull. We infer dark energy from the expansion history. The question is not whether we like them. The question is whether the inference is the simplest explanation consistent with all data. Modified gravity is a serious attempt to change that inference. But modified gravity must also match the CMB peaks and the growth of structure. That is difficult. Some modified gravity theories can do parts of the job, but then they often reintroduce something like dark matter in another form. In other words, the universe seems to want some extra ingredient, whether it is matter, a field, or a change in gravity. Now let us return to plasma ideas, because there is an important distinction. In standard cosmology, plasma physics already matters. In the early universe, before recombination, the universe was a plasma. The sound waves that created BAO and CMB peaks were waves in that plasma. In galaxy clusters, hot gas is plasma. In jets from black holes, the plasma dynamics are crucial. So mainstream cosmology is not blind to plasma. The disagreement is about whether electromagnetic forces dominate gravity on the largest scales, because electric charges tend to neutralize on large scales, and because gravity is always attractive and adds up. The mainstream expectation is that gravity dominates large-scale structure. If plasma cosmology wants to compete, it must show how electromagnetic effects create the observed large-scale patterns without violating constraints. Now, another alternative idea people sometimes mention is that the CMB might be local, perhaps from dust in our galaxy. But the CMB is incredibly uniform across the sky, and its dipole anisotropy matches our motion relative to it. It is also seen by multiple instruments and has a clear blackbody spectrum. This makes a local origin very unlikely. So in practice, the CMB is one of the least flexible facts in cosmology. Now we can step into a deeper philosophical point. Even if the Big Bang framework is correct, the phrase Big Bang can mislead. It can make people think the model claims to explain the ultimate origin. But many cosmologists would say the Big Bang model explains the evolution of the universe from a very early hot, dense state onward. It does not necessarily explain what came before, if before is even a meaningful word. So when someone says they reject the Big Bang, they might mean they reject a singular beginning, or they reject inflation, or they reject dark energy. It helps to be precise. Now let us name a few alternative positions more clearly. Position 1. The universe expanded from a hot, dense state, but there was no singular beginning. Quantum gravity replaced it with a bounce or a smooth transition. Position 2. The universe expanded from a hot, dense state and inflation happened. But inflation is part of a larger eternal picture where our observable patch is not the whole. Position 3. The universe expanded from a hot, dense state, but our understanding of gravity is incomplete, so we may not need dark energy or dark matter in the same way. Position 4. The redshift is not mainly due to expansion. Something else is causing it. Position 5. The CMB is not primordial. Something else made it. The first 3 positions are the ones where most serious alternative research lives. The last 2 are much harder to support because they must replace multiple pillars. Now, if you are listening late at night, you do not need to carry all these categories in your head. You can let them settle into a single calm idea. Science is a process of narrowing. Many possibilities exist at first. Then the universe gives constraints. The constraints do not care about our preferences. They cut away the weak ideas and leave the ones that can survive. And even then, the survivors may not be fully correct. They may be approximations waiting for a deeper theory. Now, there is one more alternative angle that deserves a quiet mention. The idea that time itself could be emergent. In some quantum gravity approaches, time is not fundamental. It emerges from relations between states. If time is emergent, then asking what happened before the Big Bang might be like asking what is north of the North Pole. In such a view, the Big Bang is not a start in time. It is a boundary of a description. This is not an alternative you can easily test with a telescope, but it shapes how physicists think. Now, as we come to the final stretch, we can return to the sky and let the technical details fade into a softer image. Imagine the universe as a long river. The standard model says the river once passed through a narrow canyon, hot and bright. Alternatives ask whether the canyon was truly the start of the river. Maybe there was a bend before it. Maybe the river loops. Maybe it comes from a different source. Maybe the canyon is a feature of our map, not of the river. What we can say with confidence is that the river is flowing. The galaxies are moving apart. The background glow fills the sky. The light elements carry a signature. And beyond that, the origin remains one of the deepest open questions. So tonight, we do not need to choose a side as a belief. We only need to understand the landscape. We can respect the evidence. We can respect the open questions. And we can let the mind rest in the space between knowing and not knowing. Before we end, there is one more reason alternatives stay alive in modern discussion. Not because the core pillars failed, but because some measurements do not perfectly agree. In recent years, cosmologists have discussed something called the Hubble tension. The Hubble constant is the present-day expansion rate. You can estimate it in two broad ways. One way is to measure distances to nearby galaxies and supernovae, building a ladder of distance measurements outward. Another way is to measure the early universe, especially the CMB, fit a model, and infer what the present expansion rate should be. These two methods have given values that do not perfectly match. The difference might be due to unknown systematic errors in the measurements, or it might hint at new physics. If it is new physics, it could mean something about dark energy changing over time, or extra particles in the early universe, or other modifications. This is not a reason to throw away the Big Bang framework, but it is a reason to stay curious. There are also discussions about other tensions, like the growth of structure. Some surveys suggest the universe might be slightly less clumpy than lambda CDM predicts. Again, this could be measurement issues, or it could be a hint. These small disagreements are exactly where alternatives can be useful, because they propose different mechanisms that might resolve them. Some models introduce early dark energy, a component that briefly affects expansion before recombination. Some introduce additional neutrino-like species. Some modify gravity at large scales. These are not replacements for the entire story. They are edits to the script. So the universe is not at rest. Neither is cosmology. And in that moving space, the most honest conclusion is also the most calming. We have a strong map. We have a few areas where the ink is still wet. And we have many minds working, slowly, carefully, year by year, to compare prediction to sky. If you hold that image, you can let the details drift away. A faint microwave glow, a redshifted galaxy, a supernova that fades more slowly because time itself is stretched across distance, a cosmic ruler stamped into the distribution of matter, a handful of helium forged in the first minutes, and beyond all that, the quiet mystery of origins. If you ever want a simple way to judge a cosmology, you can ask one gentle question. What would you expect to see if it were true? For example, a steady-state universe expects no strong evolution of galaxy populations with redshift. But we do see evolution. A tired light universe expects no time dilation, but we do see it. A bounce universe might expect certain patterns in the statistics of fluctuations, and those are being tested. A modified gravity universe might expect different lensing signatures or different growth rates, and those are being tested. Science moves when predictions meet measurements, and often the best progress comes from models that risk being wrong. Because a model that cannot be wrong cannot teach you much. This is why the Big Bang framework, despite its mysteries, remains central. It made strong claims. It predicted a background glow, and that glow was found. It predicted a pattern of light element abundances, and that pattern was found. It predicted a universe where large-scale structures grow from tiny ripples, and surveys see those ripples. Alternatives are welcome at the table, but the table has rules. The rules are observation, consistency, and clarity. And in the long run, the universe itself decides. So tonight, you can rest with that steady truth. We live in a cosmos that can be measured, a cosmos that can surprise us, and a cosmos that is patient enough to reveal its story, one photon at a time. In the years ahead, new instruments will keep pressing on the edges. Better galaxy surveys will map the large-scale structure with finer detail. New measurements of gravitational waves may add a new way of listening to the early universe, not through light, but through ripples in space-time. Better studies of the first stars and the first galaxies will clarify how structure began, and improved tests of fundamental physics may tell us whether dark matter is a particle, a field, or something even stranger. If any of those results point to cracks in the standard picture, alternatives will become more than thought experiments. They will become candidates, and if the standard picture continues to hold, the alternatives will still have done their job. They will have forced the tests to be sharper. They will have kept the assumptions honest. Either way, the same quiet rhythm remains. Question, prediction, measurement, revision, and then, slowly, understanding. And there is a softer lesson too. When we talk about beginnings, we are touching the edge of what the human mind is built to picture. We are creatures of local time. We remember yesterday. We plan tomorrow. We are used to stories with a first page. But the universe might not fit that shape. It might have a beginning that is not an event, but a limit. It might have a past that is not a line, but a loop. Or it might have a deeper description where time is not the first ingredient at all. So it is okay if the idea stays slightly out of reach. Some truths are approached, not held. So for now, we let the alternatives sit on the table like quiet tools, not as slogans, not as teams, but as ways of thinking that can be tested, refined, and sometimes set aside. And we let the night do what it does best. We let the mind unwind. We let the breath slow. We let the sky remain vast. And if you wake tomorrow with one simple thought, let it be this: the universe is readable, even when it is not fully understood, even when the first page is missing, even when the ending is unknown. It still leaves clues, and we can follow them, slowly, carefully, with patience for uncertainty, with respect for evidence, and with a calm wonder that never runs out, because the oldest light in the sky is still arriving, and every new measurement is another page, another sentence, another quiet archive record. And for tonight, that is enough. Enough to think, enough to rest, enough to let the darkness feel kind, and enough to carry one last gentle question into sleep. What else is possible? In the quiet, we listen. This was a quiet archive story, where the story ends, sleep begins,